It's a great day for Gauss-Bonnet Video 3. Today we're going to talk about curvature, Gaussian curvature, and geodesic curvature. We're really just going to share some examples that give some intuition, nothing too rigorous. Here's Murphy. Oh, there he is. He's got curvature. He loves Gauss-Bonnet theorem. Okay, let's jump right in. Welcome to It's a Great Day for Gauss-Bonnet Video 3. I'm your host, Brad McCoy. So last time, what did we do? We stated the theorem, or a version of the theorem, and we talked about surfaces. So we're going to take this m that appears 3 times in this formulation of the theorem is a surface. So this will be the interior, this will be the boundary of the surface. And really we're interested in, most of our examples will be on the plane or the sphere, and we sort of compared some similarities and differences. For instance, if you have 2 non-parallel lines in the plane, they intersect once. Well, in the sphere, they intersect twice. And we got a nice formula for the area of a polygon on the sphere in terms of the interior angles that'll be useful to us later. So this feedback is coming from myself. So I made the claim that every polygon with n vertices can be triangulated with n-2 triangles. And this is an inductive proof. And what we want to do is find some sort of bisector that allows us to chop our polygon into 2 simpler polygons and then use an inductive argument. I was a little bit, my example was too simple, and my proof was a little bit incorrect here. So let's revisit that briefly. So what we want to do to find this bisector is take the convex hull. So here's our convex hull. Oop, let's try that one more time. So let's say that's our convex hull, close enough. And we're going to take a point on our convex hull, and we're going to look at its 2 neighbors, and we're going to ask, is the triangle formed by connecting these 2 contained in our polygon? So here we would say no, because we have this violation. But if I were to have chosen a different vertex, say I chose this vertex down here, and I looked at its 2 neighbors, then here I have my chop, and I can decompose this polygon into 2 simpler polygons. One of them is just a triangle. But if I'm in this situation where the third side of this triangle is not contained in my polygon, well, then what I can do is I can move as far in the orthogonal direction of the third vertex as possible and take the point that is furthest in that direction. So I want to go this direction, and I want to take the point that is not on the convex hull furthest in that direction. So in this example, that would be this point, and then if I connect that, this will be my bisector. And so then I can decompose my polygon into n-2 triangles. So a little bit clearer. Wanted to revisit that briefly. Okay, so our agenda for this video is we're going to define a few more symbols in the Gauss-Bonnet theorem, namely this K, which stands for Gaussian curvature, and K sub G, which is geodesic curvature. So this is going to be on the boundary of our manifold, if it has one, and this is going to be on the interior of our manifold. So the purpose of this video is just to give some intuition. There are lots of other resources out there that are more rigorous than I'm going to be here. I'm going to mention 2 of them. One is a book by De Carmo, that's Differential Geometry of Curves and Surfaces. A lot of what I talk about in these videos is coming from that book. And also Keenan Crane's Discrete Differential Geometry videos. I said videos, but it's also a book, so book plus videos. Maybe I'll put a link to those in the description of this video. Okay, so we want to give intuition for Gaussian curvature and geodesic curvature in this video. So Gaussian curvature, well, let's first consider a curve in the plane, and we're going to parameterize it by gamma of t. And we're going to say this is parameterized by arc length. So as t goes from, let's say, 0 to 1, we'll just move along our curve. And what do we want to say? What we want to say is some points here we would have big curvature, and maybe a point here, we'd have less curvature, small curvature. And we also want to distinguish between curving to the left and curving to the right. So this would be like small curvature left whereas this is big curvature to the right. So this tells us our curvature should be some sort of signed quantity. And we can compute a derivative, and that'll give us a tangent vector as we move along. So maybe our sign should be, what side of the curve is this tangent vector on is a nice way to think of sign. And if we parameterize by arc length, that means our tangent vector has length 1, and so we can say, well, this is x prime squared plus y prime squared is equal to 1. And then differentiating both sides, we'll get 2x prime x double prime with the chain rule plus 2y prime y double prime is equal to 0. And what does this tell us? This tells us that gamma prime dot gamma double prime is equal to 0. So our second derivative is going to be perpendicular to our curve or our tangent vector. So this is going to be gamma double prime here, or gamma double prime over here. And really what we want to look at is how much is our curve turning. We're looking for the rate of change of our tangent vector. So we want a rate of change of tangent vector. And you'd think, well, that's well and good, but do we want some intuition for what that might look like? And the osculating circle provides great intuition. So if we were to approximate these curves with a circle, so if I approximate this curve with a circle here, well, this will have big curvature will give us small radius of our osculating circle. So we'll say R1 is small. So we want this to be big curvature, so we'll say our curvature here is, let's say this is P2, curvature P2 is going to be the reciprocal of this, so 1 over R1 here, whereas if I'm at this other point, let's say this is P1, we'd have a big circle, so this is R2, and so our curvature here, P1, would be 1 over R2. And we'd think, well, what should our intuition be, or what do we want to have happen? Well, we want, if we have a straight line, that should be 0 curvature. Well, here we'd have an infinite radius on our circle, so this would be 1 over infinity, if that makes sense to you. And what else? So the straight line should have 0 curvature, so we'll say this equals 0. We'll put some quotes there. And what else would we want? We'd want the unit circle to have curvature 1 would be a nice thing. So that would be a 1 over 1, which would give us 1 is exactly what we want. Okay, osculating circle, great for intuition. So if we're in the plane, you can think of, well, how the reciprocal of the radius of the circle that best approximates the curve will give you great intuition for curvature. And we can compute it. There's a nice formula. So often in our applications, we're going to start with the sphere of the plane, so we know the curvature. So sometimes we don't even need to compute it, but in some cases we do, and just know that nice formula exists. We can compute the curvature. Okay, so what happens if we have a surface? Well, the same thing, just up a dimension. So most of our surfaces are going to be parameterized, so we'll have some nice formula, and that's okay. And again, we'd want this, the curvature of the plane should be 0, and the curvature of the sphere, unit sphere, should be 1. And if we have a bigger sphere, you should think, well, that should have smaller curvature, and it does. So we could think, well, that's just defined the osculating sphere, but there's an issue here. What if we have some sort of saddle point? How are you going to attach your osculating sphere here? It's not exactly clear. For example, I could put a sphere above my Pringle chip, or I could put it below. Both of those would seem to make sense, and it's not clear which is the correct way to do that. And so if these are not exactly symmetric, what should our curvature be? So we want a more rigorous way to compute curvature. And so what we're going to do is we're going to say I want to compute the curvature at this point here in my saddle. Well, we could consider two little linear independent paths, curves going through that point, and we could find a tangent plane. So here's our tangent plane. It would intersect the saddle and sort of this X. And once we have our tangent plane, we could define a normal vector. So using some cross product that we saw in our calculus classes. And then we could take a plane through this point that contains our normal vector, and we could spin it around. So we're going to say, okay, let's go take our normal vector, and we'll take a plane that contains this, and we'll sort of rotate it around. And for each one of these, we're going to intersect our surface on a nice curve. So here we would get a curve like this. Maybe I'll extract what this curve would look like. So this would be maybe some parabola that opens down. And as we spin this around, we could say, well, where is the curvature of this normal section maximized and minimized? And I claim this would be the minimum. And if I go perpendicular, what would be a nice color? How about green? We would get sort of a concave up curve here. So if I extract what that curve would look like, this would be our max. And then we can use our formula from curves in the plane to compute the curvature of these curves. And so let's say this is a K2, and these are our principal curvatures. K2 and K1. So this is maybe the max, and K1 is the min. And then we could define our curvature to be the product of these as the Gaussian curvature. You could also consider the average of them, but we're going to consider the product. So what would that mean? Let's say this has curvature -1 and this has curvature +1, since one is opening up and one is opening down. That would be our saddle has negative curvature. And we could verify for the sphere that we're going to get curvature of 1, and for the plane we're going to get curvature of 0. And again, with our other check, if we have a larger sphere, we would get smaller curvature, and that's exactly what we want. So, okay, so we can get our curvature of a surface at a point. We can compute that in a nice way. All right, but for intuition, osculating sphere is great, but not always. If we have negative curvature, it's not exactly clear how to attach that to our surface. So know that we have a rigorous way of computing curvature everywhere. Okay, so we could use this to get a taste of the Gauss-Bonnet theorem yet again, something called total curvature. So if we have a triangle on our surface, so here we have a triangle on the sphere. I believe we saw this in the last video as well. We can relate the sum of the angles to the integral of the curvature over the triangle. So here, if we're on the unit sphere, we know that the curvature everywhere is 1, and if we take this specific triangle would be 1/8 of the sphere. So the total area is 4 pi. If we divide by 8, we get pi over 2. So if we integrate this thing, curvature is 1 everywhere. We're just going to get the area. So on the right-hand side, we're going to get pi plus pi over 2. And on the right-hand, or the left-hand side, pardon me, all three of these angles are right angles, so we'll get 3 pi over 2. And we see that this formula checks out. So I'm not going to prove that, but it's sort of a hint at the Gauss-Bonnet theorem. We could also consider triangles in the plane. So what do we have here? Here our curvature is 0, and the sum of our angles is going to be pi. So we'll get sum alpha I equals pi plus 0. So that checks out. And if we're on a surface with negative curvature, notice our angles are going to be smaller than pi. So we're going to get a negative value here, which works out there. So that's total curvature. Okay, so now we're going to talk about geodesic curvature. So if we have our statement of the Gauss-Bonnet theorem, what we're going to do is we're going to add up the Gaussian curvature in the interior of our surface, and we're going to add up this geodesic curvature along the boundary of our surface, if it has one. So if you think of the sphere, there's no boundary here. So maybe this this term might not even exist. Okay, so geodesic, it's not bad to think of this as a shortest path or shortest arc between 2 points. So in the plane, if we have 2 points, what does a shortest path look like? Well, it's a straight line. Well, on the sphere, if we have 2 points, what does a geodesic look like? Well, it's a part of a great circle, or a circle that goes the whole way around the sphere through the antipodal point. And so those are 2 examples of geodesics that hopefully are intuitive to you. And so geodesic curvature is how far is a curve from being geodesic. So if I have some curve that's not a shortest path, we want to sort of quantify how close is it to being geodesic, and that's exactly what geodesic curvature computes for us. So if geodesic curvature is 0, that tells us it's a shortest path. Okay, so what we're going to do is we're going to parameterize a patch of S. Oh, I got to be careful here. I'm overusing S. Let's say S is our surface. And so then we're going to consider a curve moving through our surface, and we can compute a tangent vector to that curve and a normal vector. And then we're going to take the cross product of those 2 things to get this third vector that we'll call S. So what are some properties of S? Well, it's going to be perpendicular to our curve. It's going to be tangent to our surface because it's perpendicular to our normal vector. And it's also going to be perpendicular to t here. So those are some nice properties of this vector S. And our geodesic curvature is going to be the rate of change of the tangent vector towards this vector S. And again, usually we'll have some parameterization of our boundary, and we get a nice formula. So we can compute this in most of our cases. We either know it or it's going to be computable. That's not going to be an issue. In a nice example to keep in mind, I found this on Austin Christian's notes, I believe, when he was a TA at UCLA for differential geometry, and this was provided great intuition. So consider 2 curves on the sphere. Let's say we're on the equator, and then we'll look at when we're horizontal but up north a little bit. So if we take our tangent vector, we'll get something that's perpendicular to the xy plane. And if we take our normal vector, let me get a different color. Again, we're going to be horizontal to the xy plane. I believe I misspoke there. So this is going to be n. And so if I take our vector S is going to be pointed in the z direction. So this is going to be S. And what I can do is I can project the equator onto the plane spanned by T and S, and I can look at the curvature of that. And if we do that, we'll see this is going to be a straight line, and that's because we have a geodesic. Now, if we consider this northern curve, let me stick with my color convention here. Well, we can get our tangent vector, get our second derivative, and then we can look at this vector S. Well, it's no longer going to be pointing vertical because it's in the tangent space here, or it's tangent to the sphere, so this is not vertical. And then if we project this curve onto this plane, we'll get something that has non-zero curvature. So geodesic curvature is the planar curvature as it would be measured by an inhabitant of the surface. So you want to imagine you're a person on the earth or an ant on the sphere, and if you're walking along this curve, how would you measure the planar curvature? Well, if it's a great circle, you would say it's a straight line, so that would be 0, whereas if you're up here, this is not going to be a great circle, so that should have some planar curvature, and you can measure that by projecting onto a tangent plane and computing the planar curvature. Okay, so let's summarize what we did in this video. We filled in a little bit more of the Gauss-Bonnet theorem. We talked about a Gaussian curvature, and we're going to integrate that on the interior of our surface. And we talked about geodesic curvature. We're going to integrate that on the boundary of our surface. Two important things are the plane. The Gaussian curvature of the plane is 0, and for the sphere, the Gaussian curvature is 1, the unit sphere. And then this geodesic curvature is measuring how close is a curve to being shortest path. And this example from Austin Christiansen's notes is great to keep in mind for some intuition about geodesic curvature. It was a little bit difficult for me to understand when I first see it, and still maybe a little bit difficult to understand. Okay, next time what are we going to talk about? Well, we only have one piece in the Gauss-Bonnet theorem, namely the Euler characteristic. So we'll talk about the Euler characteristic and how the first example we saw of Pick's theorem is actually a special case of the Gauss-Bonnet theorem. So I hope you tune in for the next video. Certainly a great day for the Gauss-Bonnet.